get started. Go ahead, take out your notebooks. I'm not going to ask you to copy everything off the screen directly. I'm going to try to point out some things on these slides. All right, so we just witnessed an example of miscibility, two liquids that are miscible in each other, meaning they can mix. And when we saw that, we added 50 milliliters of 95% isopropyl alcohol with distilled water. When we added 50 and 50, we ended up with an overall volume of 95 milliliters rather than 100 milliliters. So part of the reason why this worked is because both of these substances were polar molecules. So in solubility equations and in solubility concepts, when we're talking about making solutions, we have this expression where we say like dissolves like. This is very important. Whenever we say that, what that means is you have to have two molecules of the same type. All right, so if it's a polar molecule, a polar will dissolve a polar. A nonpolar will dissolve a nonpolar. If we mix a nonpolar molecule and a polar molecule, it will not dissolve. Now, so moving forward, we have this idea of like dissolves likes, and we saw the example where we mix the alcohol and water. Both of those are polar molecules, so they will dissolve. Now, I have distilled water in the beaker here. Distilled water is a polar molecule. Water is always polar. And then I have some mineral oil. So when I pour the mineral oil in here, and it's going to be kind of hard to see, but what do you notice that the oil starts doing? All right. It goes on top, and actually as I poured it in there, it made little globules and went back up. Oil is a nonpolar molecule. That means in its bonds, it does not have a positive or negative end. So they're both very clear, but if you look at it closely, you can see that there is a layer right around the 120 milliliter mark, and that is the separation between the oil and water. Now, I mean, I can take it. I don't know if I'm going to be able to do this, but no, globule is the word. All right, so something else that you can see happening here, the dye that I just put in here, the dye is also a polar molecule. So the dye went straight through the oil, and it's not starting to spread out until it gets into the water. So we see the dye starting to dissolve and spread out in the water.
That is so cool.
All right. And again, that has to do with like dissolves like. So the dye again was polar, so it dissolved in the water. The mineral oil is nonpolar, so it's not going to dissolve. Now, I did that kind of slowly when I mixed it, but if I mix it kind of rapidly, we can get the oil to mix in there, but the oil is going to then separate back out pretty quickly. Yes? Yeah, I would just have to find another polar molecule that is less dense than the oil. All right, the water is more dense than the oil, so the oil is going to go on a layer on top. So obviously the dye and the water are more dense. And so if I found a lower density liquid, like maybe vinegar, I'd have to look up the density of it. Maybe something like antifreeze or something like that. I don't know. I'd have to look it up. But it has to be polar, nonpolar, polar, nonpolar, polar, nonpolar. If you get two polars together, they're going to mix. All right? Yes. Because the dye is got a similar density to water, so it must be more dense than the oil, so it falls through. Guys, I'm going to ask that y'all stop. All right, so really the main thing that I want you to know here is this expression, like dissolves like. So polar substances will dissolve other polar substances. Non-polar substances will dissolve non-polar substances. All right, and this directly relates to one of the terms that you had today, and that was electrolyte. An electrolyte is when you take something like an ionic compound and dissolve it in water. Basically, if I were to take a battery, or if run an electric current through the water that's in here, distilled water. Distilled water will not conduct electricity. So in order to make water conduct electricity, we have to add some sort of electrolyte, some sort of salt. All right?
Distilled water on an electrical fire?
Yes.
Awesome.
Pure water will not conduct electricity. The reason why we're used to water conducting electricity like a swimming pool or a bathtub, realize what they do to our water that comes through the tap. They add things like fluorine and chlorine to it. Fluorine, and they don't just add pure fluorine or pure chlorine, they add a fluoride, a salt, to our water to purify it.
There's lead in our water.
Some amount. There's also copper, there's magnesium.
Magnesium?
All right. Yes.
I have a question. This is about to sound stupid, but it's a realistic question. Whenever I go to Mississippi, their water straight stinks. Is it
Um,
true?
I didn't know what to report. She tells me when to record.
I tell it too. All right, so talking about solubility again, just some other factors that affect the solubility. Temperature and pressure are going to determine if something dissolves or not. And we're going to look at this in relationship of a graph and see some things that happen. But typically, if we have a solid being dissolved in a liquid, as we increase the temperature, the solid becomes more soluble. Oh, wow, you're moving it around. So as we increase the temperature, typically we can add more solid to it to get it to dissolve. The opposite happens whenever it's a gas in a liquid. So like when we're trying to inject carbon dioxide into Coca-Cola to make it have the fizz and all, they actually have to reduce the temperature of the liquid. So the lower the temperature gets, the more of that gas that can be injected. That's why if you have like a 2 liter of Coke, it's better to keep it in the refrigerator because it'll hold that carbonation longer. It'll keep from going flat as quickly.
That's why I'm on a flight like 2 days.
So if you leave a Coke out and once you open it and that pressure is released and the carbon dioxide starts escaping, if you don't want it to go flat quickly, you need to reduce the temperature of it so it can hold more of it in there. Yes?
You know what? That's a great idea. You know what? Since your science abilities and my sales abilities, we should open a grocery store again.
I
It should be called Jim Martin's grocery store.
will have to see.
Sell magnesium.
You could have like a section of the bag where we sell like for a week. And it's
All right. So moving forward. All right. So this is the statements I want you to have. In general, the solubility of a solid solute increases. Solid solute increases as the temperature of the solvent increases. And then know this statement as well. in general, the solubility of a gaseous solute decreases as the temperature increases. The third statement, I'm not going to ask you this on a test, but the solubility of a liquid in a liquid is generally unaffected by temperature. So temperature does not change the ability of a liquid to dissolve in a liquid. However, temperature does affect the ability of a gas and a solid to dissolve. So a solid in a liquid, it is a direct relationship, and in a gas in a liquid, it is an inverse relationship. So solid in a liquid, temperature goes up, solubility goes up. Gas in a liquid, temperature goes up, solubility goes down. All right, so guys, gentlemen, so when we're talking about solubility, we have something called a solubility curve. So when we're looking at this, and we just made some statements about temperature in its relationship to the solubility of a substance. So one of the things that we can notice, all of these are salts being dissolved in water. So again, since it is a salt, it's an ionic compound. Ionic compounds are very, very polar, are extremely polar. So we see this relationship, all of this, guys. One of the things I want to point out is this statement right over here on the side of the graph. It should say it on yours as well, but it says solubility grams of a salt in 100 grams of water. What do we know about water at standard pressure as far as 100 grams is equivalent to what volume? All right, so let me say it like this. If the density of water is 1 gram per milliliter at standard pressure, what would, if we had 100 grams of water, how many milliliters of water would we have? 100. All right, so basically what this is saying is we have X number of grams of any salt that is dissolved in 100 milliliters of water. All right, so let's kind of look forward at this, and this should be the same graph that you have, or a very similar graph that you have. All right, so let's look at this one on the screen. To determine the solubility of one of these salts, we need to first determine the temperature of the solvent. So at what temperature is the water at any given point, and then draw a line over the solubility. So if I said that I had water that's right at 30 degrees Celsius, so we want to find the solubility of lead 2 nitrate. Lead 2 nitrate is this one, PbNO3, 2 molecules of NO3. The temperature of the solvent is 30. So I'm going to do like a dashed line, or I'm going to find the 30 degrees Celsius line. And then the next thing is I'm going to find the point where this line crosses the graph. And that's going to tell me the solubility. So this intersection is where the solubility is. All right, so about how much lead nitrate can dissolve? About 65 grams. So I would say on my answer on the test or something like that, I would say about 65 grams of PbNO3 2 will dissolve in 100 grams of water at 30 degrees Celsius. All right? So, does that make sense how to read that? What about if I asked it in reverse? What if I said how many grams of KCl, potassium chloride, will dissolve? Well, let me back that up. At what temperature could we dissolve 50 grams of potassium chloride?
Wait.
At what temperature could we dissolve 50 grams of potassium chloride? All right, so we go across right here at the 50 line, and we see that it is right around 80 degrees Celsius. All right. Couple of things that you need to pay attention to on this graph. When the intersection is on the line, that is saturated. If the amount of substance is above the line, that is supersaturated. If the amount of substance is below the line, that is unsaturated. All right? So what I want you to do... Huh? That is the solubility curve for whatever substance it is. So we have different salts on here.
Wait, how'd you know it was 80? Where where?
Yes. So I said I had, at what temperature will 50 grams of this dissolve? So I found where the line intersects, and I said it's about 80. It's actually a little bit less than 80. It's like 78.
So, at what temperature?
What did you come up with for sodium nitrate at 30 degrees Celsius? All right, I got about 96. And again, when you're doing this, it is perfectly acceptable to make this little line here like this, and that tells me that you're saying approximate value. If you don't put it, I'm not going to take off. But when you don't put it, you're saying it is definitely that amount. If you put the little symbol in front of it, it's telling me approximate value. All right, sodium chloride at 70 degrees Celsius. What did we come up with?
40.
All right, 40. So I got 39 grams. At
Unsaturated fat?
at 35 degrees, lead nitrate.
I got 70.
70. I guess it really depends on where you draw your 35 degree mark. All right, potassium chlorate at 65 degrees.
28 grams.
All right, I got 27, so 28 is pretty close. All right, cesium sulfate, I got 6 grams. Anybody got anything different? 5's close enough. As long as you're within a couple of grams, gentlemen, as long as you're within a couple of grams, it's going to be okay. So calcium chloride at 25 degrees.
90.
And just for Tyler, so cackle at 25 degrees Celsius, 87 grams. Now that's going to go out on YouTube for the world to hear. All right. I know. All right. Yeah, well, I have to put them on there so that I can link them to our website. All right. So last thing as far as notes, actually we have a little bit more. So solubility of gases is also affected by pressure. You need to know that statement. And then this second statement right here. As the partial pressure of a gas over a liquid increases, the amount of the gas in the liquid also increases. So what we can kind of think of it is if we have a container that we have a liquid and then we have a gas in here, if we increase the pressure, we're going to force more of that gas inside the liquid. So think about a soft drink when you open it. What do you always hear? All right, so you hear that sound. Why do you hear that sound?
Because that's the cack coming out.
It's releasing a gas. So inside the can, the inside of the container has more pressure than the outside of the container. So whenever you pop the top or when you unscrew the lid on a soft drink, you release that pressure. What that also allows to happen, what immediately starts happening when it starts bubbling. So the carbon dioxide that's trapped in the liquid starts coming out. So when you release that pressure, the vapor pressure is low enough that the carbon dioxide gas starts escaping back out. Yes?
So like, gotta say like you can't breathe,
So, last concepts. Molarity, molality, and percent by mass. So, we have these three equations. So for molarity, whenever you do a molarity equation, I'm going to say something like we have in the classroom right here in that yellow cabinet, I have 6 molar hydrochloric acid. So what is that really telling me? That's telling me that I have 6 moles of HCl per 1 liter of solution. All right. So I might ask you to calculate if I had 2.5 moles HCl this is the unit. So molarity, this is the unit. You can either write molarity with this capital N, or you can write it as mole per liter. All right. So what would be the molarity of 2.5 moles of HCl dissolved in 500 milliliters of water? So how would we do this calculation? All right, so it'd be 2.5 moles over 500 milliliters, but what do we need it in? Liters, so that's going to be 0.500 liters. All right, so 2.5 divided by 0.5 gives us what is our molarity? I thought you had it. What is 5? All right, so we would have 5 molar HCl. All right, does that make sense? All right, moving forward. The other calculation that we do, and the other calculation that I'm going to have us interact with today, is this one called molality. I will tell you, teaching Chem II and all of that, I have not used molality a whole lot, but it is a calculation that is used from time to time. And in this one, we take the moles of the solute divided by the kilograms of the solution. So it's going to be kilograms of solute plus, make that a little more clear, kilograms of solute plus solvent. All right, so you might have, now the other thing to pay attention to is it's important that we convert from grams to kilograms. A lot of times in your materials it's going to be given to you in kilograms. If we're using the periodic table atomic masses, it's going to be in grams per mole. So we need to put it into kilograms, things like that. So that's just, again, dividing it by 1,000 to get whatever unit. All right. And then the last one is concentration by mass. Just go ahead, get this formula. We're going to actually do concentration by mass tomorrow. I'm not going to do concentration by mass today. The only ones that I'm going to hold you responsible for calculations today is molarity and molality. But so just remember, it's mass of solute over mass of solution. This can be in grams or kilograms. That doesn't matter. But remember, mass of solution is solute plus solvent. So if it tells you that you have 50 grams of water and 50 grams of sodium chloride, your total mass is 100 grams in the solution. Total volume may not change, but your total mass will change. All right. Any questions, comments, or concerns?
No, senor.